Great. Model calibration is one of these areas I've done quite a bit of work. It's an area which is has a lot of texture to it, a lot of interesting sides to it, and it's a topic where I believe there are additional methods which can be very helpful as sort of alternatives to modern model calibration. So the basic deal here is that often when we build a model, we want to inform it with the best evidence. But a fair bit of the evidence that we have empirically is often data that can't go into just the model parameter estimates, but instead it relates to the behavior of a situation of the system as a whole. We can't simply go from the data we have concerning certain measurements from the world and just use it directly to estimate one parameter or another parameter in isolation. Instead, it's the result of system behavior that involves many parameters, many aspects of system behavior. And yet, that empirical evidence, it somehow constrains our interpretation of parameter values. It says something about the plausible values that they might have. And calibration is a process that seeks to understand the implications of that emergent data for parameter values by adjusting less well-known parameter values to best match this data. And often we're taking a single model and matching many sources of data with that model simultaneously. In that sense, it's unlike, say, a traditional regression model where we're modeling perhaps with some known functional form, some known link function. We're matching a single set of data, for example. Here we're matching many different types of data out of different model outputs, and we're doing it with a model specification that merely defines implicitly model behavior instead of giving an explicit form like using a logit or a probit model or using a linear regression model that presupposes some response of the dependent variables. Okay, so calibration you can view as sort of triangulating from diverse data sources. Basic idea is you're tuning less well-known parameter values so that the model itself best matches the observed data, and you're trying to match often against several time series. Okay, you're trying to get the model, this process, to answer the question, what must these parameter values be in order to explain all these different sources of data? Okay, and this is a very important point in the modeling process because it's often here that we learn that our model just doesn't cut it. Models are not arbitrarily malleable. Models cannot be twisted into whatever form we want by twisting parameter values. The model structure, as we say in system dynamics, determines the behavior. There's only so much wiggle room it has. We may adjust parameter values over a huge range, but have very little hope of having the model match the data. And that's going to tell us something. That's where we learn. We learn something about the situation we didn't know otherwise. We learn something that will help us refine our model structure assumptions. So in many modeling projects I've been on, it's at the calibration process that I learned that things don't add up. My mental model of the situation is not consistent with the data, and this is where I go back and refine my model. This is where I go back, recheck my assumptions, re-examine my boundary a bit, and potentially change this or this one thing or this other thing in my model.
Would it be fair to say that if you use it just to rely on your calibration, if your logic of your model and you're missing important, well, I mean, without knowing, but if you're missing some important parameters or you didn't think about it, then the logic of your model is not without it, and then you don't get it with you don't conform it to the real data. And if you try to use calibration in this circumstances, it will calibrate it, but it will mend it without that important parameter. That means it will change known parameters to
This is actually very true. If you sometimes leave out an important parameter, example would be you leave out networks from your model, network structure, and you try to get your model to kind of match the data. In some cases, it will be able to match it by adjusting other parameter values. So it will affect the contact rate. And this is a known phenomenon for infectious disease models that I believe it was Robert May, maybe together with Anderson, wrote about. You know, how there can be, you can capture, by adjusting your contact rate, you can kind of get it to behave as if it has a more heterogeneous network, for example. And so if you assume a homogeneous network, classic random mixing assumptions that you have with an aggregate model, that people just kind of mix together without any special affinity, any special long-term association. If you run a calibration with a model like that, and it's really, in fact, a highly heterogeneous network structure under the surface of the real world, what you will find is that it may pop out in form, it'll overestimate the contact rate, for example. And so it'll sort of, you squeeze it here, it pops out there. But sometimes, and quite often, it just won't match at all. And that's what tells you, okay, there's something wrong here. It's not adding up. I need to re-examine my assumptions. But although I must say, in a number of cases I've encountered as a modeler, there have also been cases where it just doesn't add up. It does not add up. I try varying my assumptions. It's still not working. And I'm mystified. And, you know, I'm thinking our model has to be rethought maybe in a fairly profound way. And I go and I talk with the people who are the domain experts, and they say, oh, don't worry about that. We redefined the definition of a kindergartner in that year to include the last year of preschool. And that's why you see this big jump, you know, in the data. Or we redefined, you know, during those years, those specific years, they had a broadened definition of what constitutes a TB case to include incipient TB. And so it was redefined category. And as a result, the data was hugely skewed for those couple years. And so they said, basically, you can, you know, those years, it's a different definition. Don't treat those the same as the other years. And so this is what will often highlight certain issues with the data that otherwise would have gone unnoticed. So that can also occur. So let's talk about a little bit of the how, and then we'll examine this. So calibration uses this optimization algorithm. It's an optimization algorithm in the sense that it tries to adjust parameter values to minimize a discrepancy between what the model predicts and what the actual data shows, what the empirical data shows. Okay? Here we're picking some sort of what we call objective function, some sort of way of measuring that discrepancy, saying how bad is this given run, and we're trying to minimize that badness. So we specify what to match, we specify how much we care about different matches potentially, and how we judge discrepancies, what parameters to vary, and then any other characteristics of the optimization algorithm. So here we're adjusting different assumptions about different parameters. Here we have mu at the bottom, tau, and beta. We're adjusting them and trying to find that sweet spot that best matches the empirical data with respect to our assumptions about these parameters. Okay, I don't have time to go into this in detail, but I do want to show you how this is accomplished. And you can find multi-lecture sessions of me on this material online, okay, where I deal with it in several different lectures. Okay, ladies and gentlemen, we already have this model loaded, so I'd like you to go now, instead of at this parameter variation run, I'd like you to go to the calibration area. And you'll find in the calibration area a set of different displays. This too will be running the model many, many times, but with different parameter values, as well as many times for a given set of parameter values, okay? So here we're going to have displayed up on this graph the discrepancies over time. On this lower graph, it's going to be trying to match historic data, which will be shown in yellow, with current output from the model and the best matching data from a particular run of the best matching set of parameter values. Okay, so here we go. So, oops, I ran the wrong one. Sorry. I wanted to run calibration. Raheem, would you mind getting me a bit of water? My throat's really not good. Oh gosh. Oh, I modified this model. Sorry, I deleted a bunch. Oh gosh. Now I'm really in trouble. I'm in a pickle. Okay, no TA is going to help me with this. Okay, you folks can run the model while I go remediate my situation. I know exactly what I did 2 weeks ago in North Carolina. Boy, am I in deep trouble here. Okay. So I know what I have to do, but it's going to take some time to do it. Okay. So what you should see on your screen involves a set of data. Thanks a ton. A set of data that is varying over. So that it's showing 3 different curves, and over time, it's trying to draw the 2 curves close to each other. Okay, now I'm in trouble. What do I fill in here?
You're in the middle of deleting it?
Yeah. Yeah. Okay, this is bad. Okay. Yeah, it doesn't fix it. Oh gosh. Okay. Yeah, that'll be. No, this is the one in the example model. It saved it modified. I knew it. This is one of about 4 times in my life I've regretted saving too frequently. Okay. Okay, this is going to be a long process. Okay. So maybe we could declare a break for a few minutes. And could one of the TAs email me a copy of this model? SAR, agent-based calibration. Sorry.
It's the same example model that's provided by AnyLogic.
Yes, but it's modified. Sorry? I need the original one. So you're mailing it to me? It's in all models to the right-hand side. Scroll down. Okay. Okay. Again. Okay. Great. So, folks, what you should see when you run this model is something along these lines. You see successive attempts to find solutions, and you'll notice these solutions shown up here as dots on the screen indicating that successive attempts. The best one thus far is this one at the bottom here, and it's trying various combinations of parameter values and trying to find the one whose average match to the data is the best. Average across many what? Many particular runs, so many realizations, many things that have the same parameter values, but they differ with respect to the stochastics. It's trying to get the best average match against the data. And you see it's settled on something that's pretty close to the underlying yellow data. It's getting successively better, but it's kind of tweaking around the edges right now. So in this sort of calibration, what's going on is that we're trying to match historic data, and I'll briefly show you how this is incorporated, and then we're going to have to move on to other topics. So the basic deal here, folks, is that you have a set of historic data, empirical data, one of whose time series is shown here. Now, in my challenges, I've asked you to try modifying this so you examine multiple sets of data. You try to match simultaneously against multiple data time series. And my students in my class here actually go through an exercise to do exactly that. But For this particular case, we're just matching against a single time series over time, and that's defined in this so-called table function. Table function allows you to specify graphically and with respect to empirical data, mapping from one axis to another. You could plot it out there. So let's go to calibration here. The calibration experiment, which includes that historic data, if you scroll all the way down, you'll find that table function we just looked at, that table function called infectious historic here. That table function is something which is used to fill up a data set. This data set, infectious historic. This lives in the experiment. This, in other words, it occupies the experiment, and it's filling it from this historic data into that data set. This is just a table function. It's something that defines it. Here we're filling into a data set. And then before each run, we clear away things that relate to the sort of outcomes of that run. And after each particular realization, after each particular run with a certain set of parameter values and a certain random number seed, it reads from the output of main, hence root, and it fills up an internal data set. That data set is then used up here, further up, to compare with the historic data. And it evaluates this difference function. Now this difference, this is described some in my slides in a little bit more detail, but basically it takes the square root of the average of square difference between the data sets here. Basically it takes the square root of the average of the square difference between the two of them. And so it's similar to sort of a classic metric for sort of distance metric for the length of a vector. So here it basically compares these two, reports the degree of discrepancy, and then this is the thing we're trying to minimize as specified here. Now, having done that, if this iteration, after having run many realizations, maybe 10 of them for a given set of parameter values, if this is the best one thus far, then it fills up this DS infection best, which is the data set to hold the best outcome here. It fills it up from one of them. Okay? So it fills it up from one sample, one of them. And in order to judge whether it's the best, it takes the average, sort of the average difference, the average across all the different realizations in the discrepancy. So this is what's testing if it's the best iteration. So in short, it's running main many times. After each run of main, it's using a particular set of parameter values. It's rescuing the outcome from that experiment, saving it away, using that to judge how closely that run matches the historic data. It's doing that several times, using replications 5 times per parameter, a combination of parameter values. And then, if the mean over those 5 has been the closest thus far, in terms of judging the difference, if the mean of them is the closest, then it records it as the best one thus encountered. So that's how that runs. It's trying to find the best of parameters, and it's recording those best set of parameters up in this area. It's recording I stopped it here. It's recording the best encountered set yet. Okay, so this is calibration, trying to match model results against empirical data by adjusting parameter values. And traditionally, what you adjust is the less well-known parameter values. Okay? So any questions about that? Yes?
I'm assuming that you're defining a number of locations rather than defining steps of your parameters, that it's just randomly picking from those parameters, it's randomly picking the number from your ranges. So I assume that these are called capacity this way, is not currently running?
No. There is some stochasticity, particularly in the outputs here, but it's actually not picking randomly among these parameter values. It's actually performing a fairly sophisticated optimization algorithm to modify these. I believe it's based on genetic, some sort of genetic algorithm where it's trying to combine the best, sort of if it gets various best results from different runs, it tries to combine them together to yield the.
So there's some underlying process there.
Oh yeah, it's a quite sophisticated one. It's based on the OpQuest engine, which is a widely used engine, used I think also by Arena and other simulation packages. So this is based on OpQuest, which is viewed as best of my knowledge, it's viewed as quite a competitive optimization algorithm. I believe it's significantly more sophisticated than in some other simulation softwares, and it's adjusting these parameters within these acceptable ranges. So within these ranges, 0.5 to 5, 0.1 to 8 to 0.8, it's adjusting these to try to find the best match within that. That make sense? Okay. It also, although I don't go into here, you'll find me talking about it in other videos. You can also impose what are called constraints and requirements. These basically, the constraints allow you to say, so you specify these legal ranges for parameters, but you can further say things that don't involve any one parameter. For example, maybe A plus B plus C. 3 parameters have to total up to less than 1. And if that's not true, then it won't run that. It won't consider that case. You can also look at the model output and decide whether or not that's acceptable. So for example, if you have a stock and flow model and a stock goes negative, a physical stock of some sort, count of people, then you would throw that out because there's probably been a numeric error of some sort. So you can specify requirements which dictate results after running the model, tested after a simulation model run to see if that's a legitimate output. Okay? So during the optimization, it's adjusting parameter values at a conceptual level. It's adjusting these points in space here. It's going around this in some sort of clever way, trying to find a combination of values that moves on average across multiple realizations, multiple replications, as specified here. It on average best matches the historic data. That's what its job is of the calibration. Okay, any questions about that? Okay, you'll find me multiple lectures on where I discuss this in more detail. And as I said, I have little exercises where you can elaborate this to additionally match other things, not just one time series. My students tell me that that's really helped them understand the process much better once they've actually tried modifying it, tried adjusting it, and getting it to work with other types of data and so on. That's what really allowed them to fully understand what was going on here. And it's been my experience, you really want to work with it in a hands-on way before you'll really understand it. Question?
I was going to, now that after you've calibrated, you deem the calibrations are acceptable, then would you use those parameter values in the model and you were looking to project something?
So, yes, although there's multiple steps that are described in my slides a little bit that you want to be careful of, because you want to make sure that those are that you're reasonably confident about those particular values, that there's not many possible values that yield just about the same results. And if so, you'll want to sample among different possible parameter values. So the folks at StatsCan, for example, interestingly, use they have different terminology. They use the terminology parameter sweeps for what we were describing as sensitivity analysis before, but they use parameter variation to describe sampling around parameter values. So rather than using one privileged set of parameter values, they'll actually sample around them stochastically and run the model with those samples. And you can do that very easily in AnyLogic. I didn't describe this earlier, but it bears noting, and this is maybe worth a nugget, is if you go to the parameter variation experiment back here, I should have emphasized this, but it slipped my mind. Up here, if you say, for example, freeform, I could actually specify, for example, a draw of this, in a very tight distribution around the value 15 with a standard deviation of 1 or something like that. And that would actually now draw different values for this parameter from a tight distribution. And they'll sometimes do that. There's differences in the modeling community for how firmly you adhere to the calibrated values. Jushin and I have been doing work under her guidance related to use of Markov chain Monte Carlo techniques for these sort of models, where rather than calibrating and then just assuming some best match parameter values, you instead use the empirical data to arrive at a posterior distribution for the different parameter values, and then you sample from that posterior you arrive at, in the sense that you can sample from it. And by sampling from, you could actually sample from it, like when doing an intervention, evaluating an intervention. Then you get a distribution out for the incremental gains of that intervention vis-a-vis baseline. And that's something to which I'm very attracted. I'm wary of putting all my eggs in one basket with calibrated values, but it's extremely common to do so within the simulation area. It's just, be aware that this area which is really evolving in terms of thinking about how best to do it, and there's different sub-communities with their own sense of what's acceptable, et cetera. Is that helpful? Okay, yeah, sure.
Clarification question. This calibration example has been in AnyLogic for a long time, and are going through the agent-based models. Does the same framework apply to doing calibration systems?
Yeah, it would. Yeah. The difference with system dynamics models would be if you're talking, system dynamics models are commonly deterministic, and if you're using them in a deterministic way, you wouldn't be using replications. I'm looking at the wrong thing here. You wouldn't be using replications because there'd be no need to run it many times. It would yield exactly the same results. For parameter variation,
we're looking at ranges of parameters.
Oh yeah, you would use it. You could do that, right? Right, yes.
In a more formal way in capture.
Although you still wouldn't use replications. What you'd be using for that is you'd be using this mechanism up here where you would specify a draw from a distribution, and you wouldn't be using replications. But yeah. So for a system dynamics model, you would just do a very similar thing, but not use replications, and it would adjust it. And I haven't compared VenSims versus AnyLogic's results, but I think AnyLogic's algorithm is much more sophisticated than VenSims for the calibration. So I wouldn't be surprised if it's superior, but it may not be quite as fast as VenSims, because I think I won't launch into uber geek mode, but But what happens behind the scenes in Vensim is that it achieves a way of running it quickly. I wish I could tell you. I'm sorely tempted, but I don't want to alienate people. Yeah.
Right? I can imagine one in both of these experiments in a lot of models that one builds.
Yes.
Other than just doing it from the ground, is there any shortcut way of grabbing these and putting them up to the bottom?
Sorry.
Any shortcut process for importing these into a model?
You mean these variation experiments? Oh, it's not that bad. Oh, it's. I know it looks like a lot of mechanism. It's really not that bad. It's just to set these things up. I mean, I create parameter variation experiments. I could create it in a new one in 10 minutes for a parameter variation experiment to get it to display some things, and that's what we did in North Carolina. You can go watch the video. Maybe it took 15. I don't remember the exact amount, but it's pretty quick. It takes 15 if I have a class with me, right? And because I have to lead it through and make sure everyone follows and so on. But no, it's not that bad. Calibration is a little bit more involved, but really you're filling in little things in a picture that's already there, and it's pretty stock boilerplate code for most of it. So it's pretty structured in terms of what you have to do. It's not that bad. Yeah. Is that helpful?
Where are you going somewhere like if you like here in this model, there's a calibration experiment and like a custom experiment there.
Yeah.
If we want to start from scratch.
Yeah.
That does not have that.
Yeah.
Where do you go? Like,
okay. Yeah, I'll show you. It's a good question. So here's our little model from the morning. I could do file, new, experiment, and here I could choose a parameter variation experiment or a calibration experiment. That's a pretty.
Oh, I see. That's most of the.
Yeah.
but why is the Monte Carlo blanked out there?
Monte Carlo, depending what version of AnyLogic, I think it's enabled for certain. Although I will note this, that if you have these example models, you can always copy from one and paste it in another.
Well, that's what I'm saying. You're going to change file layout, but you can do copy and paste.
You can do copy and paste.
Cool.
Yeah.
I think I'm finding any easy way.
Yeah. And edit. Yeah. Yeah. Yeah.
Educational versus you can only have a simulation
Yeah, you can copy and paste. Yeah? Yeah, I think it's okay. I don't know if there's any problem with it, but yes, you can copy and paste it. Yeah. Yeah. Yeah, question? Yeah.
I'm sorry if you already
No?
addressed it.
Yeah?
But when you were looking at, when you pulled up the new experiment,
Yeah.
there was optimization and calibration.
Yeah. So, okay, it's a good question. A calibration is, so at a conceptual level, I would have to go and look for those particular ones, but at a conceptual level, a calibration is to compare against data. You're trying to optimize to match your model output with data, and so that you have a very specific goal in mind of matching some empirical data. Whereas optimization in general, you might be trying to gain, instead of trying to get a best match to data, you might be trying to find the policy, for example, which yields the best results. And so what you're actually changing is policy-related parameters that will achieve, the best match between cost and savings to get the most favorable dollars per quality adjusted life year saved or something like that. And so you'd be optimizing it to yield the best outcomes rather than to best match the empirical data. Does that make sense?
So why, when this is called a calibration?
Yeah. Yeah, the term of art for how to respond to that in computer science is called mumble. I honestly, this is something I've been meaning to do for a while, but it looks like, it'll set it up for you to sort of, for how you want to sort of do these, any criteria, so you can set it, be in some range, contact rate in some range, and I'll set it a minimum value of this and a maximum value of 10, and looks like that, and looks like I don't know why it's unhappy. It's oh, you want to say that the time, so the simulation output and the observed data. So I'm guessing they did it by hand before this was available, and now it looks like it's a little wizard, and it probably, I'm guessing maybe it outputs an optimization experiment, just all pre-configured to match your data, something like that. Yeah. But the short answer is I don't know, and I haven't investigated it, and we probably should, but it looks like it's that sort of thing.
So the
Yeah.
parameter variation
Yeah.
is that we can use the calibration was grayed out.
Oh, okay.
But what you're saying is you can create it
You could copy it and paste it from
from the other.
that model.
Okay.
So,
Yeah, I guess that's one of the differences between the
yeah.
university.
Yeah. Oh, I've done most of my work with the lower versions of AnyLogic, so that's what I've done in the past when I needed it. So, yeah. Yeah. So they don't allow you to, I don't think it's by accident. I think it's just there's a convenience, it'll be there, but you don't have access to it. All I could say is I'm glad you can copy and paste it. Okay. So, anyway, any final questions on this? These are some good questions. Okay. Okay. So.